Okay, so good morning. For this third lecture, I will mostly talk about sheaves, derived category, and singular support. So I said that the sort of vague goal is to have this correspondence between sheaves on one side and Lagrangian submanifold on the other, and so I'm going to describe today mostly the sheaf side and how you go from the sheaf side to the Lagrangian side. And then, of course, the question is how to go in the other direction. So first, let me remind you that pre-sheaf, well, you can have pre-sheaves of basically anything, but I will be interested in pre-sheaves, let's say, of vector spaces or modules. But vector space is even good enough. So this is on a space, topological space X. This is just a map which to each open set U associates a vector space F of U. And now if U is contained in V, so there's the map here. If U is contained in V, there is a restriction map, RVU, from FV to FU, which has the usual property of what a restriction map should be, so that RUU is the identity map, and if you compose two restrictions, you get what you should get, so that R WV composed with RVU is RWU. So this is a pre-sheaf. And if there is the notion of pre-sheaf, there must be a notion of sheaf. So a sheaf means a pre-sheaf. And I will first give you a very vague definition, which is defined by local conditions. So defined by local condition means that if U is the union over some alpha of U alpha, and if you have elements S alpha defined over F of U alpha, so the elements of F of U are usually called sections over U for obvious reasons. If you have S alpha in FU alpha such that the S alpha and S beta coincide on the overlap U alpha intersection U beta, then this defines a global object. So if you have S alpha such that for any alpha and beta, R U alpha intersection U beta of S alpha is the restriction, coincides with the restriction to U alpha intersection U beta of S beta, then there exists, and actually there exists a unique S in F of U such that RU U alpha of S is S alpha. Okay. And from now on, I will not use this R notation here. I will just use the restriction notation. So I just denote RU U alpha of RUV, let's say of S, as a restriction of S to V. It's going to be more convenient. So some examples, which you certainly already know, means a number of them you already know. Well, first, any functions which are defined by regularity condition. So if you look at let's say X is a smooth manifold, and f of u is the set of ck function over u. You could also, if it's analytic, take the analytic functions, or if the manifold is a holomorphic, take the holomorphic functions. I mean, all these obviously satisfy this condition. A second example that is going to be a pre-sheaf but not a sheaf. So if you look at, let's say, CB0 of UR, which is the set of bounded functions yeah, that should, okay, on U. Well, here I put C0, so continuous bounded function on U. Well, this is a pre-sheaf. Essentially because the restriction of a bounded function is another bounded function, but is not a sheaf, because if you have any function, let's say on Rn, if you take a continuous function on Rn, if you just take a covering of Rn by bounded set, then the function is, of course, going to be bounded on each of these sets, but it's not globally bounded. Okay, so being bounded is not a local condition, it's a global condition. And so analogous to one, any solution, well, any set of solutions of a linear PDE is a sheaf. So in particular, when you look at holomorphic functions, you could say, well, this is just the solution of the d-bar operator, okay, which is a linear operator, and so they make a sheaf. Okay. But you can take just any linear PDE. Okay. I mean, this defines locally a condition, and if you have a function which on a union of sets satisfies your partial differential equation, then it's going to satisfy the equation globally. Okay, so that's another example is the constant sheaf, well, first over x. So k of x of u. This is the set of locally constant functions on u. Is there a question? You had a question? Because I say that I want to have sheaves of vector spaces. Otherwise, you would get. But indeed, if you don't ask anything to the so k sub x, which is the constant sheaf over x, is defined by kx of u, is the set of locally constant functions on u. And I insist on the locally constant because you want to have, again, a local condition. So being constant is not a local condition, because if you have a disconnected set and you have two different constant values, but when you look locally, you cannot make the difference between this and the constant function. Okay? If you have if u is the disjoint union of v and w, and if you have a constant a on v and a constant b on w, okay, this is going to be the obtained by this procedure from gluing the constant a on u and the constant b on v. Okay, and so this has to be an element in the sheaf. So the locally constant function have to be inside. So if you put just constant function, you get a pre-sheaf, but you don't get a sheaf. Now, if you have a set Z in X, then you have also Kz of U, which is the set of locally constant functions on Z intersection with U, which is another sheaf. Okay. Now, once you have this, you have morphisms. So morphism between sheaves F and G is a family of map from phi-u, Fu to Gu, and this has to commute with restriction. So if you have well, let's still call this R, even though it's not the same sheaf, so not the same restriction map. But this diagram is supposed to commute. And I also defined germ at some point is F sub x is the limit for x in U of f of u. So this is just, well, exactly the definition of a germ for function. Let me make a remark, is that if you have a pre-sheaf I'm not going to go into the formal definition, but the idea is pretty obvious. I mean, you just look at functions which locally are in the pre-sheaf. So you make local something which is a priori not defined locally, and you can do that. I mean, you can write down the formal definition. That's not very difficult. And on the other hand, one has to be a little bit careful because the same objects are defined for sheaves and pre-sheafed and have a different meaning. So one important point where one has to be careful is in the definition of kernels and images. So assume you have a morphism of sheaves, which I will write like this. Okay. What's the kernel of phi? Well, the kernel of phi, you want this to be a sheaf. And so you should say for any set U, what is this? Well, there's an obvious definition, which is this. Just take the kernel of the map phi U. And this is good. Where things are a little bit more complicated, it's here. Not because of bad will on my side, but just because this does not define a sheaf. Okay. Well, that's easy to see because if you have what would you need? So let me see what the notations are here. Assume I have just two open sets, U and V, and sigma is phi U of S, tau is phi V of T. So S and T are in F, sigma and tau are in G here, so are in the image. And you assume that sigma is equal to tau on the overlap. Well, the question is, can you glue together sigma and tau to be the image of something? So is sigma the restriction of phi of U union V of something restricted to U and the same for tau? Well, what's the obvious way of doing that? Well, you should say, well, to do that, I have to glue S and T, of course. But there's no reason why S and T should coincide on the overlap. The only thing you know is that phi u of S and phi v of t coincide on the overlap, but S and T themselves don't have to coincide on the overlap. So there's no way a priori, and even a posteriori, to construct an object here in F, okay, such that the image is going to be sigma on u and tau on v. Okay, so that's, there you're stuck. And so the only thing you can do is to say, well, the image is still a pre-sheaf, because this restriction property still works. And what is this image here is actually the sheaf associated to this pre-sheaf. So that's one slightly delicate point. So I'm going to use the language of categories. So we have the unpleasant situation where in the categories of pre-sheaf, the image of a morphism has one definition. It just would be the image of phi of u here. But in the category of sheaves, the image has a different definition. You have to take the associated sheaf to that. Okay. But it doesn't matter here because I'm only going to talk about sheaves, not of pre-sheaves, I mean, except very locally. Okay. So when I say the image of something, it's always going to be the image in the sheaf sense. Okay. So the one important notion here is the notion of exact sequence. And somehow the situation is not as bad as, so I have a sequence of sheaf morphisms here. Let's call this phi and this psi. And of course, it's exact, well, at least exact here, if the kernel of psi is equal to the image of phi. So here, the image is in the sheaf sense as before. Okay. Now, so the good news is that this is equivalent to the fact that for any x, this map here is exact, where phi x and psi x are just the maps induced by phi and psi at the germ level. So let me give you an example of an exact sequence which will be useful. So I take a smooth manifold omega k of u is going to be the set of k forms on u. So the ramp forms. And so this is essentially the ramp complex. So this is just the differential of forms. Here I have the inclusion of constant into the functions. And I claim that this is an exact sequence. So you could say, well, in this sheaf category, well, you could say, well, this is a joke because if this is exact, then it means there's no de Rham cohomology. But that's not what I mean. What I mean is it's exact in the sense of sheaf, so in this sense here. And what does it mean? Well, I have to look at germs. So let's just look at one piece here. And what am I doing here? Well, I'm looking, this is just the limit over u of omega of the k minus 1 form over u. This is the differential. This is also, again, the limit of omega k of u, and this is, again, the limit of omega k plus 1 of u. Now, forget somehow about the limit. Just think of a sequence of sets u, and because I'm in a smooth manifold, I can just take balls. So take u to be a ball, and then in this case, the Poincaré lemma just tells you that this is indeed exact. So this is exact by Poincaré lemma, and then an argument which uses the fact that you have cofinal sequences of balls as neighborhood of X. Okay, so you can tells you that at the level of germs, this is going to be exact. Okay. And indeed, the whole idea of the cohomology for sheaves is to somehow see the difference between this exactness at a completely local level and the fact that if you take a set, if you take a given open set U, or if you take the wall of X, then the sequence is not exact. Okay. Well, you just take this image of phi of U. This is a pre-sheaf, and to any pre-sheaf you can associate a sheaf. And the interesting point, which I did not mention, is that if you go from a pre-sheaf to a sheaf, then the germ does not change. Okay, so the germ at one point is the same for the pre-sheaf and the sheaf. Okay. So next, unfortunately, I have to talk a little bit, as little as possible, but a little bit, about abelian and additive categories. Well, it should be the other way around. So the good news is that there's a theorem which is due to Fried and Mitchell, quite old, which says that you may safely think about a category of R modules for some ring R. So this theorem by Fried and Mitchell tells you that if you have what's called a small category, so a category such that the objects are not are actually sets, then if it's an abelian category, then it's equivalent to a category of R modules, okay. Not of vector spaces, but. And the main point here is that the sheaves form an abelian category. And the reason why I have to introduce this is because we want to study functors from the category of sheaf. So I will write SH of X as the category of sheaves to other categories. But don't worry, these other categories will essentially be either other categories of sheaves, so sheaves over a set Y, or categories of R modules. essentially vector spaces. But in order to sort of explain what one is doing, I think it's in a way easier to at least define what these abelian categories are. So category means that you have objects, so C, you have objects C, and then for any A and B two objects, there's morphism, which is from A to B, and then there's a composition rule. So if you have a morphism from A to B and the morphism from B to C, then you get a morphism from A to C. And you have, there are some sort of obvious, you have identity in the morphism from A to A, which behaves the way you expect, okay, in the sense that when you compose with the identity, you just get the same map. Okay. And so this map here is denoted as Fg G composed of F. So just think as objects and mappings. So what does it mean to be abelian? First, let's say additive. Additive means that the morphism from A to B make an abelian group. So there must be somewhere a zero element, and there's more than a zero element, there's a zero object. So that's, so there exists an object which is called zero, which is the zero object. Well, in pedantic term, people say that it's both initial and terminal, which means that there's a unique map from 0 to A is a unique map which I also denote by 0. So there's some there could be some confusion in the sense that 0 both denotes the 0 object here and the 0 map here. And the map, so here, this is an abelian group, so it should also contain a 0, and 0 in the morphism from A to B is just the composition map, from A to 0 to B. This map here is unique, this map here is unique, so you get a unique map, which is the 0. And of course, another property is that this map here should be bilinear for the abelian group structure. So to be honest, there's another property which I will not mention, is that the category has what are called products and byproducts. So essentially, if you have two objects, you have the analog of A1 times A2, which is defined in terms of functorial properties by a sort of universal property, which I will not define here, okay, which is not so important. So in the framework of sheaves, of course, the objects are the sheaves, and the morphisms are just the morphisms of sheaves. Sorry, yes, this is associative, sorry, I forgot to mention that. And this one, but the composition then is bilinear, in the sense that if each of them is an abelian group, and then if you compose F with J plus H, it's F composed with G plus F composed with H. And this is associative. Okay. And again, I'm not going to give extremely precise definition, but an additive category is abelian if, well, there are two conditions. One is it has kernels and what are called co-kernels. And the second is that this kernel and co-kernel satisfy some property some useful property. One way to state it is that any map can be factorized as follows. But I'm not really going to use that. Okay. So kernel is what you expect. Okay. So it's a sort of universal object here, so that anything that's composed with f gives 0 will factor to the kernel of f. And co-kernel is somehow the dual. So if you're talking about R modules, which is the important thing somehow to have in mind, well, the kernel is just the kernel. The co-kernel is just the co-kernel, so this is just B divided by the image of F, dual of the image. And so once you have this, you can look at functors F. So maybe I should, I should have said, of course, that in the situation, so defining the co-kernel is essentially like defining the image. You have one, you have the other. And so in the category of sheaves, of course, the kernel is again the kernel as we define it, and the image is the image as we define in the category of sheaves. And well, because this is an abelian group. The morphism is an abelian group. I guess that's the main reason. Yes, but so I'm not completely aware of how. I mean, this is in Grothendieck's work. I tend to suspect that abelian was defined before additive, but I'm not sure. Okay. Could be. There are categories, yes, but there are categories which are additive but not abelian, of course. Okay. But if you have now a functor between abelian categories, F is additive. What I should have said is that once you're in the abelian category, the important objects are exact sequences. That's maybe the thing you should remember. So F is additive if it induces a group morphism from the morphism from A to B to the morphism from F of A to F of B. By definition of a functor, the functor sends objects. So the functor F will send the objects in the first category, C1 to the objects in C2. So F goes to F of A, and it will send morphism from A1 to A2 to a morphism from F of A1 to F of A2. You want that this map is a group morphism of abelian groups, of course. So I had to say something about, no, I will say that a little bit later. So examples. Well, as I said, the sheaves over X, this is an abelian category. And what can I give you as example for functors here? Well, as a functor, I will take the set of what's called gamma u. So from the sheaf over X to, well, in our case, it will be the category of K vector spaces, which sends F to F of u. That's one example. Another example is that if you have a map from X to Y, and if F is a sheaf over X, you can define F lower star of F by F lower star of F of U is F of F minus 1 of U. And so this belongs to a sheaf, to the sheaf over Y. So you have another functor here, which is denoted by F star, which sends sheaves over X to sheaves over Y, and this is again an additive functor. And somehow these are the main two functors or the only two functors maybe that we are going to study. So if F is additive, questions? Is exact if and only if it sends exact sequences to exact sequences. That's the definition. So for example, you can see that F that gamma u is not exact. Well, that's the example I gave you before. Okay, the example I gave you, that's the only example I gave you. See, maybe you may complain about the lack of example. Let me tell you a story that shows it could be much worse. One of my colleagues was attending some lectures in Paris by someone I will not mention here. And after a few months, I asked him, well, how are these lectures? And he says, oh, they are very nice, very interesting. The only thing is that they lack a little bit of example. The only example we saw so far is the canonical sheaf on the empty set. So you see that it could be much worse. At least I have one example. So I have this exact sequence here. Okay. So this is an exact sequence in the category of sheaves. Okay. And if you apply gamma of u, what does it mean? Well, you're going to associate to this the sequence 0. Well, kx of u is just k. Omega 0 of u, omega 1 of u, and so on. Okay. And unless u is contractible, you know that when you compute that this sequence is not exact. I mean, you can have closed form which are not exact on u. So this is. So it tells you two things, is that interesting functors, I mean, if you believe that gamma of u is an interesting functor, do not have to be exact. That's one thing. And the second thing is that to understand how non-exact are such functor, in the sense that if you start from an exact sequence and you apply this functor to measure the non-exactness of this image, is an interesting thing, since it would give you here the de Rham cohomology of the set U. So these are the two points here. So however, most of the time one deals with functors which are not exact but are still either left or right exact. So f is left exact if for any exact, no, I don't remember exactly. Yes, I have to start with. So we have, if I start from the left with something which is exact, then this is exact. And you can check that if f is gamma of u or f is f star, they are both left exact. So that's somehow the only thing you have to remember from these abelian categories. Things is that the sheaves make an abelian category, and when you have functors which are additive and at least left exact, we're going to be interested in measuring the failure of exactness in sequences here. Well, you only ask, no, you only ask at the beginning. So only the beginning of the sequence remains exact. Of course, the sequence can be arbitrarily long, but you don't say anything about what happens next. After the third term, you don't know anything anymore. So you only say that the first step so it's slightly stronger than just asking that if you have an injective map, whatever it means, in this situation, the functor transforms it into an injective map. That certainly follows from this, and it says a little bit, slightly more. F sub star is only left exact, yes. The same difficulty here. Okay. So how do you define this how do you measure this non-exactness of f? So I have to say one word about injective objects, which I will immediately forget about, almost immediately forget about. So an object I is injective if and only if whenever I have a map from A so I have a map from A to B here, and I have a map from A to I, and say that the object is injective means that you can always extend the map from A to I to a map from B to I. So for instance, such diagram, G exists. So this is the sort of standard definition in a general abelian category. In our case, for sheaves, we're going to use a different object there is the notion of flabby sheaves. So flabby sheaf is very easy to understand. It means that the map from Fu to Fv is onto. So whenever you have a section on the set V, you can always extend it on the set to the set U. Okay. And here, of course, V is in U. And there's a slightly different, which is actually dual definition of soft sheaf, which are sheaves such that f of u to f of k is onto, and k is compact, of course, contained in U. And by definition, f of k is just the limit for the open set containing k, maybe not V, containing k of f of V. So you should think of f of k as the set of germs in the neighborhood of the compact set K. So examples, and now I have to try not to get confused because there's sort of duality. So soft sheaves are, for example, CK function on R, differential forms, and so on. And flabby sheaves are distributions on U or currents on U. So why, for instance, why is this soft? Well, if you have, it's almost by definition. What is a CK function on a compact set? Sorry. Well, by this definition, it means it's a CK function on a neighborhood of your compact set. Okay? Defined on a neighborhood. Then you can apply, I don't know, apply some cutoff function or whatever, but in any way you can extend it to a bigger set U, always. There's always an extension. Okay. Of course, it's the same for the forms. Okay. And for the distribution, it's sort of the dual argument tells you that this property holds. Okay. And in our situation, even though flabby or soft sheaves are not injective, it's injective sheaves which are flabby, okay, it will be good enough to do everything with flabby or soft sheaves. Okay. You don't really need the injective sheaves. On the other hand, if you go and look in any book, you will see that everything is done in terms of injective sheaves, which are injective objects, okay, because this is the objects which are defined in any category. So what's the idea now? Well, now I want to have a resolution of an object A. So resolution means I have an exact sequence here. And I will assume that all these sequences terminate at some point, just because it's easier. So A is just any object. And IK are injective. But if you don't like injective, let's say you want to stick to the category of sheaves, then you just take the IK to be soft sheaves. Or flabby for this reason, but in our situation, it will be soft. And then what do you do? Well, you look at this sequence here. You have a functor F. Now, this is not an exact sequence anymore, so it has cohomology. And then you define Rj of f of A to be the J cohomology of the above sequence. So this should be exact, of course, here. Depends what category you're looking at. Okay, most of the time, and in the category of sheaf, you can ask that it terminates, and it's a little bit more convenient. But formally, you don't have to require that it terminates. So this Rj of f of A, by definition, is the cohomology of this sequence.
That's the resolution.
No, the resolution is this thing here. So I don't know what's actually the formal term here, Rj f of A is the, it's not the derived functor. What's the, I forgot what's the term for the J cohomology. The derived functor is going to be something a little bit more complicated, but is the, well, let's say, right derived functor for f at A, something like that. Exactly. So that's the theorem, which I'm not going to prove here, is that the definition is independent from the choice of the resolution. And even if you're using flabby sheaves or anything, the crucial fact is that you take two such resolution, okay, and you look at the identity map from A to A, and by using this property here of extension, you actually build a map from I0 to J0 to I1 to J1 and so on, and you get a morphism, and eventually you show that this is going to give you an isomorphism in cohomology, because it's going to give you a chain map. So that's the idea. So there's a slightly different way of seeing this. Well, maybe let me give an example which I already gave, somehow always the same example. Is that the example I wanted to give? No, let me give a general example. Sorry. I have a sheaf F. So this is in the category of sheaves. I have the sheaf F, and then I take a resolution by injective or soft or flabby sheaves, doesn't matter. And then I apply gamma of u. So I'm going to get 0, f of u, I0 of u, I1 of u, and so on. And the cohomology of this is, by definition, well, that's a possible definition, the J cohomology of u with coefficients in F. That's a way to define the cohomology of a sheaf. Start from a resolution of the sheaf, apply this functor sections over u. Okay. So to say that this is exact, so at the beginning it's exact means that at each point this is an exact sequence, okay, but of course not on an open set U. So you look at an open set U here, and you get the cohomology. So in particular, special case, of course, H0 of U And F is just F of U is the set of sections over U. That's one way to define the cohomology of sheaves. So that's an important thing because, as you can see, it's on the right lower corner of the blackboard. And sub-example, of course, well, I take the Durham resolution for the constant sheaf here, so omega 0, omega 1, and so on. And what I get is that the J cohomology of U with coefficients in the constant sheaves, which should be just the cohomology of U, is indeed equal to the Durham cohomology of U. Because you have to apply sections over U, so you have omega 0 of U, omega 1 of U, and so on. This is just the Fourier differential. And what you get in the end is the Durham cohomology of U, and this is the same, by definition, as the cohomology of U with a coefficient in Kx. More questions? But that's because it's left exact. So if you apply the, so what it is? It's under, of course. So you start from this here, 0, F, I0, I1, and whatever, who cares? And here you have 0, F, F of F, but that's F of U. So F of U, I0 of U, I1 of U. So what I claim is that this, so the cohomology at this level here should be what? Should be the kernel of this map. Sorry. Yes, sorry. I think I made a mistake in the definition. Yes, of course. Let me check for a second. But yes, of course. So this is all this is wrong. You have to skip the first term. I forgot that. Hein? Oui, donc il faut enlever le premier terme. Sorry. Yes, no, it's in the definition of homology. So the homology is the, and Rj is the same for Rj. Well, let me, that's maybe worth going back to the. Here. And here. And now I can safely hide it again. So what you know is that this sequence is exact. So this is exact because, I mean, just the beginning, not after that. And so this tells you that the kernel of the map from I0 to I1 is exactly f of u. So the kernel of the map from I0 of u to I1 of u is the same as f of u. And thanks for the question. Okay. So, okay, this is nice definition. Unfortunately, you have to do something a little bit more complicated, which appears naturally, and then you have to replace objects by complexes now. And that's how you get to the derived category. In fact, I already somehow did that because I somehow replaced f by this sequence I0, I1, and so on. So one way to see this construction is to say, well, I had f here. I take a resolution. And then in the resolution, I apply this functor f to this resolution and compute the cohomology of that. So what's behind it is that we replace f by this sequence here. And then we apply f on the left-hand side. And so on. And compute cohomology. So you're actually doing two different operations. One is to replace f by this resolution. So you're replacing f by a complex and apply f. That's one operation. And the second operation is that you're taking the cohomology of this. Okay. But there's a sort of general philosophy that if you replace, if you take a complex and take its cohomology, you're sort of losing somehow information. So that doing this second part maybe is not optimal, and so that the interesting part should be the first part. So one way to see the first part is as follows, is to say, well, I have this f is the same as this stupid complex here, 0 f to 0. And here I have a second complex. Okay. So my resolution is just this one here. My resolution is 0 f, I0, I1, and so on. And if you look at the induced mapping, so you have two complexes and you have map between complexes. And you can see that the map gives you an isomorphism in cohomology, essentially because this is exact here, and because this map is the kernel of the other one. So this is an isomorphism in cohomology. So what you did, if you think of f of the object f as just this trivial complex, is that you replace this trivial complex by a much more complicated complex. So it's more complicated because it's a longer complex, but it's simpler because the objects in here are injective or flabby or whatever. And then you apply this functor f. And you could say, okay, so I'm starting with a single object, and what I'm getting is a chain. So it's a chain complex. So maybe I could do the same thing starting from a chain complex and getting maybe a chain bicomplex. And then I could do the same and start from a chain bicomplex and get a chain tricomplex, and then from a chain tricomplex, a chain quadricomplex. And the good news is that you only have to do that up to chain bicomplexes, or actually even chain complexes, and then you can sort of go back to just having complexes and sometimes bicomplexes, but nothing more complicated than that. So the idea is that if you have a category C, you can associate abelian category. You can look at the chains over C, which is the category of chain complexes. So this are something like that. 0 is A1, A2. So here I'm only taking, again, I'm only taking bounded complexes because it's simpler. You can take unbounded or bounded from the right or bounded from the left. Doesn't matter, but bounded. So these are complexes and with maps D0, D1 such that dj plus 1 composed with dj is 0. So the chain complexes. And then it happens that the chain complex also has a resolution so let's go back to sheaves. So I'm going to have a sequence 0, F0, F1, F2, and so on, Fk to 0. And then what I can do is to make a square grid here. I have to get the indices right, but so let's say this is a D map, this is a delta map. Okay. So each vertical direction is a resolution. Actually, you have to ask more complicated condition than that. But all these are resolutions. So this should be, let's say, I0, 0, I1, 0, I2, 0, and so on. And here you have I1, 0, I1, 1, I2, 1, and so on. So all the verticals are resolutions here. All the vertical and the horizontal commute up to sign, maybe. And so you get a sort of big square, which is the resolution of this object here. But the good news is that there's something which is called the total complex. So now you have something with two indices, and this is just the direct sum of I PQ for P plus Q equal n. So let's denote this by Tn. So you get a total complex, and the boundary map here, capital D, is D plus or minus delta. So you can sort of group these objects by sort of diagonal columns, diagonal directions, and you get a complex here. So this complex is made of injective objects because each of these were injective or flabby or whatever. Or soft sheaves. No, you remove the first row from the total column. Yes. You always have to remove the first column, as I did before. Okay. I did before, I just have F0, and then I remove this. Okay. So you have this. And now it's quite easy to understand what you do with your functor f. So if you have a f is a functor, and you have your complex f star and d, well, you replace f star and d by t star and capital D, and apply f. And you get a new complex, ft and fd. And this is going to be an element in the chain category of something where the image of f lives. So f, of course, has to be an additive left exact functor. And you actually can do that. So, of course, there are a number of things to prove. In particular, you have to prove that it does not depend on the choice here of the resolution. Okay. And for that, you have to impose stronger conditions than the ones I mentioned to the resolution. But the important thing is that all these objects are injective. Okay. Sorry? Oh, yes, f has to be, as always, f is a functor. F is additive and left exact. As always. Now, wait, I said that this does not depend on the choice of t, which is, of course, not correct. If you took the cohomology of this, then it would be true. If you take the cohomology of this complex, it does not depend on the choice of the resolution. Okay. However, if you take two such resolutions, what you will get are two complexes which are ft and fd, which are actually chain equivalent. So that's essentially what the derived category is. So the derived category, let's say, well, of C, this is essentially going to be the complexes of injective objects modulo an equivalence relation, where the equivalence relation means that objects are chain homotopy equivalent. So that's a very gross description of the, I mean, any. There's probably no specialist of derived category in the audience, otherwise I would have been shot already. So the idea, you would say, well, why do we make this thing so complicated? You could just take the cohomology of the objects and then that's it. And in the end, that's what you always do, almost always do. I mean, you do a certain number of construction, and in the end, you're going to compute the cohomology. Okay. What's convenient in this situation is that if you took cohomology from the beginning, then you would get very complicated spectral sequences and spectral sequence of spectral sequence. I mean, you would enter into lots of spectral sequence argument. Here you can just take this object. So if I compose with another functor g, for instance, I can just apply it directly, okay, to this resolution. And so I can see what happens. And in the end, of course, I'm going to take the cohomology. And in the end, usually I'm going to actually obtain spectral sequences. But if you wanted to take cohomology from the beginning, you would sort of be in a slightly complicated situation. So example. Well, now we can say what is the cohomology, not of a single sheaf, but of an exact a sequence of sheaf. So if I have a sequence, so we have sheaves like this, then we can define what's the cohomology of U with coefficients in F in this complex. Okay. So I think I have almost enough to go forward now. There will be some more. No, sorry, what I forgot to say is that this So this operation here is called RF. So the map which sends this complex, well, yes. To ft star f of d is denoted R of f. So this is the right derived functor. So if f is a functor from an abelian category A to an abelian category B, R of f is a map from the derived category of A, what's called B. And B means bounded to the bounded derived category of B. And how is this defined? Well, from this definition, it's sort of obvious because you have replaced A by an injective, by a chain complex which is made of injective objects. You apply F, and you get something in here, and you look at its equivalence class in the derived category. Derived category are essentially complexes of injective objects modulo this equivalence relation. So this map means you take an injective complex here, you apply F, okay, and you get a sequence here. And I should have said, yeah, okay. And so, of course, when this RJF, there's also this RJ of F, means just computing. So I start from the derived category here. I have to derive category here. And here I take the J cohomology. And, well, whatever the cohomology is going to be. Okay. So this is RJ of F is just this. And it's compatible with the previous definition if you start from an object here which is just 0F0. Okay. So now what I wanted to start to explain is the notion of singular support, which is something you can find in this book by Kashiwara and Schapira. So the definition, the idea of the definition is rather simple if you think in terms of partial differential equation. So assume you have a solution of your partial differential equation, which is defined here. And what you're trying to figure out is whether this solution can actually extend to a small neighborhood past this point here. So you have an hypersurface here, which I will denote by phi negative. You have a solution on the left-hand side of this hypersurface. You want to say, well, can I extend this solution a little bit to the right of this hypersurface? And the answer can be yes, can be no. The extension can be unique, or it could be non-unique. And so the definition is as follows. Let F be a sheaf. But actually, I can take it in the derived category of sheaves, because what I'm going to say is not only going to depend on the class here. Then the point x0, psi0 in the cotangent bundle of x is not in the singular support of F if and only if for any x psi close to x0 psi 0 and phi such that the differential of phi at point x is equal to psi, we have an isomorphism from the limit of hj of u with coefficients in f. So remember, f is actually a complex of sheaves to the limit for u containing f of hj of u intersection phi negative, again with coefficients in f. And if we have here an isomorphism. That's so a direction, because of course psi is just this. This is going to be psi 0. Now all this is made, this definition is made to say that to be in the complement of the singular support is an open condition, so that the singular support is a closed set. So that's why I don't only claim this for d phi of x0 is psi 0, but for all x and psi in a small neighborhood. Okay, but that's a technical detail somehow. But the idea is that now if I'm moving here, okay, well, why it's connected to this set? Well, remember that h0 of u and f is just f of u. So in particular, if this is just a single sheaf, what this tells you is that if you have a section which is defined here, in a sufficiently small neighborhood in phi negative, it's going to have a unique extension to a small neighborhood there. That's exactly what this is telling you. Of course, it's in the limit for small open set and so on. Of course, it's not only for H0, because that's a sort of rule in the derived category, is that if you make a statement for H0, I mean, it does not have a specific meaning, because you can always shift the indexing of the complex. So if you put a condition for H0, you have to put the same condition for all the Hj, so that it has a meaning for in this category of complexes. Okay. So this is essentially the statement for the section of U, but suitably extended to make sense in this category. And the good news is also that it only depends on the class of f in here, because this object only depends on the class of f in the derived category. So some remark. Well, maybe one obvious remark is that if you look at the zero section over the support of f, this is always contained in the singular support of f. Because if psi 0 is equal to 0, you can take phi to be identically 0. Then this set is going to be empty, and so this is 0. And so this implies that f of u should be 0 for any u. So except if you're in the, except if you're outside the support, this will always be singular. That's one thing. And then let me, in the last 5 minutes, try, well, I certainly will state examples. So if U is an open set with boundary in X, there's not enough space to write something important. open with boundary, smooth boundary in X, and then I look at the sheaf K of U, and my claim is that the singular support of Ku, well, is the set of pairs XP such that either X is in U and P is equal to 0. And clearly this must be inside because the support of K of U is exactly U times is U. And, X belongs to the boundary of U, and P is lambda times the tangents, the normal to X, and I hope this is correct for lambda negative. So this is my set U. Well, you see that if I'm inside the set, inside the open set, nothing happens. If I have a section which is defined here, this means it's just a constant section on U, then it's certainly going to extend here to a neighborhood. The only points where something can actually happen are the points here. But the points here, if I'm trying to move, let's say, if I have this direction here, you see that having a section which is defined here, it's going to extend somehow on the other side. In fact, if I'm just here, if I have a constant section, it's going to extend the other side. And the only place where I'm going to be in trouble is that if I'm just here. If I just try to extend here, then this, I mean, I'm going to how to say that? I have to find, which would be the other direction. So if I'm on this side here, you see that the only section on this side is 0, and when I move here, I have the 0 section and I have the constant section that extends. Okay, so I don't have uniqueness anymore. So if I move in this direction, I don't have uniqueness of extension. So that's one example, and example is here. So in particular, if f is a smooth function, the singular support of the set f negative is going to be the set of xp such that either f of x is negative or f of x is 0 and p is lambda times df over x for lambda negative. It's exactly the same as of what I said before. Then the second example, which is a little bit more complicated, but rather instructive, assume I have a function s over x times rk times r. I'm just stating this, and then I will stop. And look at the projection from x times rk times r to x times r. So I can take the set US, what I call US, which is the set of x, psi, and lambda, such that S of x and psi is less than lambda. So this is a set contained in x times rk times r. So I can consider the constant sheaf over US. And then I can consider the sheaf r pi star of KUS. So what's this? Well, I have this projection map here, pi from x times rk times r to x times r. So I have a map in the derived category from which sends a sheaf over here to a sheaf over here, because pi star is a functor. So pi star is a functor from the sheaves over x times rk times r to the sheaves over x times r. S is a mapping to R, yes. Sorry. So you have this map pi star between sheaves. Okay. And so you have a derived functor which goes from this derived category. So what you should say, even if you have just one sheaf here, replace a sheaf by an injective resolution, apply pi star to the resolution, and look at the class here in the derived category of the sheaves over x times r. And you see that even though I'm sort of manipulating very simple objects, I couldn't really do reasonable things without these derived categories. I mean, I couldn't define this object here without this notion of derived map. And so my claim is that the singular support of this sheaf here, of r pi star of k US, is L hat S, which is in T star of x times r. And I'm going to stop here because I'm already over time. But L hat S is essentially the Lagrangian submanifold generated by S. And that's how this relates to the previous lecture. And I'm sorry for being over time. Thanks for your attention.